Hello there, person watching today's video. Welcome back to another 15 minutes of your life in math class. Today we are going to investigate lesson 19. Lesson 19. Or if you just decided you saw the title and you thought it was interesting, solving one-step equations with adding or subtracting. Adding or subtracting. So we're going to talk about some fundamental properties of equality today that pretty straightforward, and you probably have done these before if you've ever done any equation solving or maybe even some equation building, which might be a kind of reverse engineering the problem, but nevertheless, away we go. We've been dealing a lot so far with expressions, algebraic expressions, and expressions with square roots and division and order of operations, but they're all just expressions, which means that there was no equal sign. Now, some of those things you think you do when you write your answer go equals 4, but that's you just writing down the answer. That's giving what we'll talk about later being a solution. Okay. But what we're going to talk about today is writing stuff up there and having an equal sign in the middle and having to sort things out to solve for an unknown. Now, if we start off with probably the most basic idea of an equation, as I said, equations, there it is, equal. They have an equal sign in them, okay? They have an equal sign. So something as simple as x plus 4 is an equation. It's a specific type of equation. It's a solution equation. But then you have these other ones up here. 2 plus 1, there we go. 2 plus 1 equals 3 is an equation. You see why? Let me read the official statement here. An equation is a statement that uses an equal sign to show that two quantities are equal or are the same or have the same value. Okay? A statement that uses an equal sign to show that two quantities are equal or the same or have the same value. They could be just numbers. Okay? There's lots of different ways to write 3, aren't there? You could write 6 divided by 2 equals 3. That would be an equation. It's showing that the left side and the right side of that equal sign are equivalent in value. You can rewrite them. You can then move the pieces around if it was something like that. Now, a nice thing about equations, especially if there's multiple pieces on one side, like 2 plus 1 equals 3, is that I can do something like this, and I can say, well, if I take away 1 from both sides, then I'll have 2 on one side, and I'll have the expression 3 minus 1 on the other. And that is still true, isn't it? So we're going to have today what you might call the do the same unto others. But in math, it's one of the 10 commandments of math. Do unto one side what thou doest unto the other. If you're going to subtract by 1, you're going to subtract by 1 on the other side of the equal sign. If you're going to multiply by 2 on one side, you're going to multiply by 2 on the other side. We'll prove why you're not changing the value of what you're doing. You're only changing the way that it's being expressed or the format of those things. Keep looking around from the black pen that I was doing something with. And do you see it anywhere, viewer? No. Help, help. Okay. Equations can extend to beyond just simple things like 2 plus 1 equals 3 or 2 equals 3 minus 1, like a math fact kind of thing. It can extend to something like this with just variables, and this is the ideal gas law from chemistry. Pressure times volume equals the number of moles times a constant times temperature. And the rule says that pressure times volume is going to be equivalent to, is going to have the same value as these other set of conditions if they're at the right specific values. Okay, so one way that you might want to think of an equation is being a big scale. Okay, and we know that the scale must be balanced. I have a triple beam balance scale hiding somewhere. Yeah. Oh yeah! Don't drop it! Don't drop it! And how this works is that there's a pivot over here. Okay. Alrighty. So you put something on this side, and it's supposed to, depress this, but the other side then goes up. And what right now is that this side is down, so that means that somehow I'm somewhat imbalanced, which is probably pretty normal in my case. So what I've got to do is I've got to slide these things along until the left side of the balance matches the right side of the balance. We're getting close. That's just about right. So now it's even. Pivot point's got the same amount on this side as it does on this side. Oh, and that's the way equations work. So if that's the case, if I have 5 pounds over here and I have 5 1 pounds over here, that's equal. And I can, if I take a pound off of both sides or put a pound on either side, it's still equal, right? Because I'm just putting the same amount onto both sides of two things that are already equal. Now, once we've, well, let's say, let me draw this up here. Let's say we've got something that we don't know. We'll call it x. And we know that if we added 1 to x, that it would equal, let's say, 7. Okay? So let's imagine that these two sides are balanced, and that one side is x plus 1, and the other side is 7. So if I take that 1 off of this side, and I take 1 off of that side, then I'll have x, and I'll have what it's equivalent to on the other side. I would just solve that equation. But the only way I'm gonna take away this 1 is by subtracting 1. So if I subtract 1 from x plus 1, and I subtract 1 from 7, I'll get 6. Or if I just want to leave it there, I'll have 7 minus 1, and I'll have x plus 1 minus 1. And you can see that the plus and the minus cancel each other out. And now I'd have to just do the same thing on the other side. 7 minus 1 is 6. So I found the solution to this equation in one variable. The variable being x, the unknown, the thing I don't know, the thing I'm looking for. So the rules are pretty straightforward as far as solving one-step equations by either adding or subtracting. Let me give you the formal rule. The first one is the addition property of equality. The addition property of equality says that if A is equal to B, that I can add 1 to both sides and they're still equal. At least I think that's one way to say it. If I do the same thing to both sides, well, let's not even do 1. Let's just call it some other number C. That way it can be anything we want it to be. If A is equal to B, then I can add C to both sides and it's still equivalent. I still have an equal sign in the middle of those two things. Okay? So imagine A is 7 and B is 7. If I add 4 to both sides, 7 plus 4 is 7 plus 4. That's the addition property of equality. Now the subtraction property, since those are basically the same thing, remember that subtraction is just adding the opposite of a number. There's no such thing as subtraction, but we'll just go with it anyway. All we got to do is change this to a minus sign. And that's our subtraction property of equality. If I've got two values, A and B, and they're the same, that if I take the same amount away from them, I still have the same thing. They are still equal. Okay, the subtraction property of equality. So that means that addition and subtraction are inverse operations. They undo one another. And every math system has a series of rules that determine how you do those things. What you do to something and then how do you undo those things. And just starting for starters here, addition and subtraction on the same level of PEMDAS, they undo each other. If I start right here and I take 2 steps forward and then I take 2 steps back, I end up exactly where I started from. So we're going to need that because that's how we're going to undo something that's already been done, like x plus 1. Something's been done to x, and I want to undo that so I can just have x all by itself. The inverses that we'll be looking at here would be addition and subtraction, multiplication and division, and we've already looked at squaring something and taking the square root. Okay, those are all inverse operations that or operations that we've done before that are just inverses of each other. And the book introduces one and shows you how to work with it, and then it introduces you to the other. Now that pen's really bugging me, so I'm gonna hit pause. I'm gonna find it. I'm gonna find that thing, whatever, you know. Got it. Found it. Let's walk through some problems really quickly. They've changed math books. You've been doing this since like 5th grade or maybe earlier. Okay, algebra here. Maybe they used a question mark, but it's the same thing. So let's use our property that what we want to know is what x is. It's our unknown, and I know this is easy enough that you can do it in your head, but let's do the steps anyway. If x had 3 taken away from it, we're going to add 3 to it. And if we're going to do it on that side, we're going to do it on this side. So that part equals 0, and this part's just x. Drop down that equal sign, and now we have a solution to that equation in one variable. X is equal to 15. If I went back up here and I put a 15, then it's still true. 15 minus 3 is 12. Here, k had 7 added to it to make 12, so let's take the 7 away from both sides. That leaves us just with k on this side, an equal sign, and 5. There's our solution. And so we can go back and check it and see that if we plug in a 5 there, that makes it true still. You can even do it with fractions. Okay, now fractions are a little tougher because you're going to have to manipulate them a little bit, but the fact is still true. You can think of 2 ways to doing this, but we'll just do the basic way that we're learning here. We need to take 1/4 away from both sides. Now this might be the tricky part, dealing with those fractions. But let's just make 1/4 into an 1/8 type of problem. 1/4 is the same thing as 2/8. So 3/8 minus 2/8 equals 1/8. We can verify that by going back into here and seeing that 1/8 and 1/4 equals 3/8. That's true because 1/4 is 2/8 and 1 plus 2 is 3. Now, I want to challenge you to build your own equation, which would be something like this. Start with a letter, like the letter of your name. Okay, so mine would be M. And M equals 42. And then I want you to do the same thing to both sides and rewrite this thing. So maybe I want to take away Bethan's age right now and then say, well, how old was I 15 years ago when Bethan was born? I'm going to take my age right now, which is 42. I'm going to take away 15. That means I'm going to have to do that on this side as well. So this is still true. And that means that 15 years ago, I was 42 minus 15, which is 30, 20, I was 27. That's true. All these are equivalent to each other, but what I just did was I built an equation that I can then undo to get back to my original solution. I'll put up one more thing here really quickly before we end. Just hang on a sec. One crazy weather story. January 10th, 1911, the temperature in Rapid City, South Dakota fell 47 degrees in 15 minutes. We know what the ending temperature was. We want to know what the beginning temperature was. And so we might write it like this. There's some temperature that I don't know that dropped 47 degrees and now it's 8 degrees. That's like x minus 47 equals 8. We're going to add 47 to both sides. You move all the known stuff to one side and you're left with the known on the other. Once the unknown is on one side and the known is on the other and they're equal, you've got your answer. Merry Christmas.